Good afternoon, everyone. Thank you for coming, and Happy New Year. Our speaker today is Ulas Bagci from Northwestern University, a very good friend of mine for like almost 10 years. Yeah. Time flies. He's associate professor at Northwestern University's Radiology, Electrical and Computer Engineering, Biomedical Engineering. He works on AI machine learning applications in biomedical and clinical imaging, and he has been really productive with more than 400 papers now, and he holds quite a few NIH R01 level grants, multiple of them. And he's been area chair for MICAI HB transactions on medical image analysis, and some. Also, I didn't know that you have quite a few actually best paper awards and reviewer awards from good conferences. Thank you.
Thank you very much. Thank you for the introduction, and thank you for coming in, even in holiday. Yeah, if you have questions, just stop me. We can do some interaction. So today I'll try to share some of these topics. Actually, watching knows, Kaihan know. For many years, actually, we work on this topic of human in the loop. I'm gonna show just one way of doing this with eye tracking devices, how we move forward. Many years actually we invested. I think where we come is still maybe just one small step. Hopefully we can really improve human in the loop systems for high risk applications such as in medical AI. Okay, it works. So my laboratory's name is actually Machine and Hybrid Intelligence Lab. The hybrid is coming from how we can incorporate human in the loop. Particularly, we focus on experts like radiologists, pathologists, clinicians. And nowadays, we also look for including the patients also in the loop. So that the hybrid name is actually coming from there. Some people say mixed, the intelligence. So three things actually we focus in our laboratory, three main, the steps. My students and collaborators, we work on algorithmic robustness of these AI algorithms, interpretable, explainable methods. These are, the machine learning, algorithms. And today I'm gonna talk actually some applications and algorithms that we develop, like expert in the loop systems. Mainly, we use, the eye gaze tracking systems for this topic. So expert in the loop actually systems may be, the very useful for variety of reasons. I can say one of the, the reason is that actually ethical considerations, especially these last 2 years, we look at the ethical part of, these AI algorithms from patient perspective, from doctor's perspective. In high-risk applications, putting the just pure algorithms may be dangerous. It may have some, the drawbacks. We work on, the algorithms, developing like mixed algorithms where algorithm can fail, but the human can complement those systems. At the end, many of these algorithms go to the doctors for, the double check or, the secondary opinions. Again, like recently we have some works on this, the ethical considerations and how we should really approach to the, the problem considering the human in the loop. And again, this human can be all stakeholders, including the patients. So just one example, like we have also in our group, there's one student who is a pancreatic cancer survivor, and he's also working in our laboratory as a researcher as well, undergrad researcher. So we, not only him, but we talk with many patients, but especially him from the algorithm perspective, like as a developer and as a survivor. We ask what they really need to see. The many patients actually, nowadays they find our the laboratory names. They send email to us even, like where this AI stands, the stands, and then how they can get some, the help, especially for our pancreas, the project. So many emails actually we are getting from patients. AI is very famous, it's everywhere, so we understand this, and this excitement from everybody. But the steps are really, really slow, I can say. We are not anywhere there to help them just one-to-one. So the complex decision making, again, so for this kind of application, human intuition, creativity, the expert in the loop system can be very helpful. Transparency and accountability, again, actually we have 2-3 very important, the project ongoing. This is actually, again, widespread problem. So when we approach to the disparity issues, for example, how algorithms are actually behaving, and to complement them, to correct them, expert in the loop is one way of approaching the problems. And actually, I'm gonna actually skip that one. And also domain expertise, like this explainability interpretation are really, the subjective terminology, explainability to whom, right? So everybody talk about explainable AI, which is, we also believe that it is very useful. There is this nice article by our colleague. He put a framework for interpretability. I know Kaihan has, some work on this as well. So we have, the algorithmic interpretation is something, but at the end we need also some reasoning, which is, at the decision level, which is high level. It is very difficult. We try to make our algorithms not only like visually appealing or visually explainable, but also the decisions are understood by all the stakeholders. So for this kind of things, experts should be in the loop. The guidelines can be considered like an expert. Doctors are experts. So we need to actually talk with, for every different problems, actually, we need to talk with them and define, the explainability components to make things actually more transparent. For those actually who don't know the radiology rooms, just want to give very brief explanations of most of our works are actually in radiology. And we are trying to put our algorithms and system into the radiology room, so it is better to give a little bit background on this. Usually, radiologists work in a very dark environment with limited distraction. There's a little dedicated light source. Often it is like a blue for some physiological reasons. And so what they do is actually visual search. The image numbers and patient numbers are increased a lot. So they are working even from their home. There is the teleradiology systems. People are having actually very little time for this reading, especially in the private hospitals. Reading one scan is actually very limited time compared to research hospitals. So having AI algorithms making this, the readings easier, faster, more accurate is a desirable goal. So many companies actually trying to do this. Many components, like from diagnosis to reporting. I can say there are also a lot of reporting companies like auto-reporting. When radiologists, they see something in the screen, they have this speech-to-text actually microphone, as you can see on the screen. They very fast actually they read this, and there is a template. The template is filled with the help of large language model. Nowadays it is faster, and then this report goes to the the system. And hospitals have also usually another system reading the secondary reading for whatever it is there, just to check errors and other things. So the goal is actually to make this screening the easier, faster, and the more reliable. I'll show one example like why screening is important. Radiologists are really great at reading quite fast. Just one example about lung cancer. So there are many screening cases: prostate, breast cancer, lung, the liver, so many the different the screening algorithms. Once actually when we start this human expert in the loop systems, we start with the lung cancer. The reason it is the number one the deadly cancer worldwide. But there is one way to actually help people to catch the lung cancer. As you can see, if you catch the lung cancer at the early stage, their survival is more than 90%. So, and there is this lung cancer screening available worldwide. It's a similar strategy, like there's a low dose CT scan. People who met the criteria for lung cancer screening, they got this, the low-dose computer tomography screening, and then radiologists read this. It is the same, almost everywhere in the world. And if they catch this lung cancer, actually you have a better survival rate. So it is important, you catch those tiny, small tumors. Often they look like, the healthy tissues. So this is a New England Journal of Medicine, one of the pioneer articles showing that it can be reduced. This cancer death can be reduced by screening. So many algorithms actually automatically detecting these lung cancers, lung tumors from CT scans. Some of them recently go into clinics helping doctors to measure, those tumor size and if they, go bigger or lower and helping the screening strategies. But still, radiologists are missing tumors. And this rate is not actually small. It is around 30-35%. In this, the CT scans, actually, there is one small tiny tumors. If your eyes are not trained well, actually, you may miss very easily because that tiny tumor look like, the tissue, normal tissue. It is just there. You can, really easily miss this tumor. If you catch it, you save a life. More than 90% of the, the survival rate is going to be actually increased. But why radiologists miss? This is actually psychology problem. I don't want to say problem, but there are many misinterpretation reasons. We call it bias. The bias is a correct term. This is a nice actually radiographic article showing, more than 10 reasons why radiologists may miss those tumors. Two of them actually we will focus because that is the highest number of events happening in radiology room for this particular lung cancer screening. One of them is called actually the satisfaction of search. Satisfaction of search is happening like when the radiologists see one tumor, let's say, or one abnormality in the images, and then they are already happy about what they find, and there's the passion for searching the other abnormalities is decreased. So the attention actually is already reduced. Another bias, maybe the most important one, is called inattentional bias. Here, maybe this abnormality is actually hidden in the plain sight, or they look like normal tissue. So you may not really, even they may not really actually see. So all other biases are actually here. The two of them are actually the mostly encountered. Satisfaction of search, I personally also see a lot, in our, the experiments as well. So here, for example, again, like, the 30-35% of the lung nodules are typically missed. There is one tumor here. So it's a big one. Actually, it is visible from, the saliency point of view. You can actually easily see that. But if you actually carefully, look at this CT scans, so there is one actually gorilla is hidden here. And this is actually a famous study by Dr. Jeremy Worf. He's still here. So 20 out of 24 radiologists, they missed this gorilla during this, the screening. So that is, how satisfaction of search. They find the one tumor and their attention mechanism is really changed. So this is very sensitive task, and they may miss so easily because of the many topics. Deep learning is again actually is really great. Right? It can find so many the tumors and help radiologists. But my experience in the such software and such AI tools are this: so many papers around, finding those tumors nicely. When it go to the clinics, it produces a lot of false positive. So when the doctors sit here in front of computer, there is one tumor catch, but so many false positives. They don't want to deal with this false positive. It's going to cost a lot of time. So many of those algorithms are not there yet. So the humans are great, but they can miss. Deep learning is great finding this tumor if radiologists miss, but they also produce false positive. So they have all strengths and weaknesses. So that's why we try to combine deep learning and human together to improve the computer-aided diagnostic system. So just to complement their weaknesses. So we start this, the eye tracking project in quite early 2015. So if we can, one way of combining, the experts with the deep learning. So different style, eye tracking, the system exists. At that time, it was like glass-based system we started. So the eye tracking systems, what they track your gaze information, and for a screen, they tell you where you look at and how long you take. You look at that and give you some attention maps like you see here. These systems, and in a funded project actually. Now actually more than 4 years, we are working on this project especially for lung cancer screening. We focus for the NIH grant, but we also use this for many others, the organs. We had time to test. We call it radiologist-centered AI. It's like a human in the loop. And we try to actually integrate these two brains. One of them is artificial to improve the system. So we have actually many publications. These are the main ones. I try to talk short for each of them, except the first one is pretty old. And how this story started and how we actually, going forward with the pace of, the fast pace of deep learning. I'll start with the CCAT, which is, I call it actually collaborative computer-aided diagnostic. Collaboration comes from the human and the computer collaboration. We call it true collaboration, really, because we use, their strengths and try to complement their, the weaknesses. This is our very initial setup, quite engineering way of actually doing this. So I can say that actually, before, I don't know actually before us actually if anyone has done 3D realistic radiology room tracking. I think no. I know Jeremy Wolf. He's a very big name in the eye tracking, and Elizabeth Kurpinski. We work with her as well. She's the president of this Medical Perception Society. Before us, actually, everybody was using very, the laboratory environment, very fixed, 2D images, and ask radiologists just to sit, fix, don't move your head, and just look at the screen. So that is actually putting a lot of pressure on them to do, the screening, and it is, they become nervous. It looks like, like a competition environment. In real radiology rooms, it should be dark. They can use any monitor, multiple monitors. They can use contrast, different contrast. They can use 3D, most importantly. There was no 3D tracking available. And actually, they can also change the zoom, for example. This is very important. Sometimes they draw, they draw something, they measure, they also talk. So none of these eye tracking systems were suitable for clinics. So that's why actually we work a lot to just make this happen. It's a lot of engineering effort there. So during this eye tracking study, we recorded every mouse, keyboard, and the motion of radiologists to to understand what is going on, and then just not to miss also their attention region. We start with these classical glass-based systems, and we had this eye tracker as a separate computer. And from PACS system, which is how radiologists are reading the the radiology scans from this PACS software. Every hospital their own PACS system, and it goes to the radiologists look at them. It goes to the eye tracker. It generates some the biological attention where they look at it, how much, and then we have our algorithm, deep learning algorithm, to analyze both images and these attention regions together to make the diagnosis. In light and dark environment, it can work. This system. This is from 2015-16, the initial setup. Again, like a lot of engineering effort, but it was the first real radiology room experience. Later, we develop our own software so that actually we don't need to fit everything into the, the different PACS system. Very simple software. Radiologists or any users in hospital, they don't want to really, click any, the buttons. They just want many things just to be, automated. So with this software, they can do zoom and 3D screening. They can do some measurement. They can even talk. We record, their voice as well. They can change the contrast, as you can see. So it is like, they feel like they are already in radiology room. So this is what we want. So we don't want any nervousness or any other pressure. just everything should be real or near real. We start with actually our experiments with glasses, and then we switch into this. This 4-view eye tracker is the second one actually we use, and additionally we buy actually this eye link. This is the most accurate one actually in terms of the gaze tracking. It's really expensive, the tools. A couple of them we have. Nowadays actually now we changed our direction a little bit different, and we want to do everything on the webcam. The accuracy is gonna be actually lower, but this way we can actually include many radiologists actually in the loop for our experiments. Currently, having like a few radiologists, 5 radiologists in most of these experiments. The literature shows actually the highest numbers like 8 or 10. Recently we did like 16. We are making it 20. These are very good numbers, but it is not enough. So we plan with one of these biggest the conferences of radiology like RSNA or the other big conferences. If we attract people, radiologists, we can even reach the thousands of people just to use the same software through webcam. And if we can track their eyes, probably it's gonna be really good. So two of our students are working on this the chip solutions. So there are actually lots of psychology, in psychology there are lots of eye tracking studies. So those attentions can be somehow used for analysis. So we wanted to use those attentions generated by the eye tracking in the deep learning directly. So how we can do is actually this. So we come up with this idea that the gaze is in one point, like in the pixels. And then when the radiologists look other places, actually there is actually directed graph actually they are directed search actually they are following. So we said that, okay, let's model this attention as a graph, because there is a search and it is not the entire pixels. It is only the sum of the pixels. They are connected to each other, and this is a direct. And some of the pixels can be revisited by the radiologists. So this fits really to graph theory, and we decided to actually create a graph directly from this the attention. And the G is a graph, and then we have the V and E. In a graph, you have vertices and the edges, right? So the vertices, we say fixation, like the nodes. This is the pixels. The fixation is the one that the people look at it, and edges actually the movement of the eye, right? The search. So how they move. So we can use this attention as a graph, and now the idea is actually how we can incorporate this graph into the deep learning to make it work. Otherwise, these softwares generate some attention map, it's colorful, nice, but we don't really know how they do it. They put some Gaussian information there, and show you some rough information. It is never super accurate actually. So we want the exact numbers, how many seconds they look at it, and that pixels how many times they visit it. So this way actually we can achieve this. So what we have done actually, initially we noticed that there are so many saccades and edges, so many data points there. It is difficult to analyze real time. So, and in one fixation point, there are so many pixels. So you don't really need them. So what we have done actually, we did some non-parametric clustering to reduce the number of this fixation and also these edges. You see, this is the raw data for lung cancer screening. It is a lot. So if you do non-parametric clustering, so these regions, like it is the same region, but so many pixels, you don't really need that, so we need to remove them. The same for these edges. Some of the edges are actually repeated many times. The radiologists look at the same places again and again, so we just need to define them and remove them from the system. So we also use the simple algorithm. It's called graph specification. This is a linear time algorithm. We can discuss, if you are interested in the details. So linear time algorithm to sparsify removing those edges from the system. And at the end, actually, we have very sparse graph to be included in the deep learning to do our task. As you can see, this is step-by-step, really engineering way of doing that. This was our first study. So once we understand actually these attention regions in CT scan, it goes to do multitask learning At that time, we were using CNN, like everybody else. So detecting the nodules, segmenting, and telling if this nodules is, the cancer or not. The multiple tasks were actually done. Later, we switched into capsule algorithm at that time, and recently, we also use, the transformers. Once the deep learning is advancing, we also switch our algorithms just accordingly to improve the results. So there are actually 3 different engineering components here. They are trained separately. It is not end-to-end. But it gives us, really good results. We published this in Medical Image Analysis. It's quite a long paper and, the pretty good results. I want to show these 3 radiologists how they actually read the lung cancer study, the CT scan. The first one is radiologist 1, is experienced one. Second one is the middle. The third one is actually the very novice radiologist with limited number of years of experience. As you can see, the first radiologist is also very fast in reading, just 2 minutes. The third radiologist is like, the 5-6 minutes. And this last row is the one actually we are using for deep learning input. Those regions were actually good enough just to, put it into the input, into the CT scan with deep learning to put more attention to those regions for finding the lung tumor. Okay, so this is an engineering approach again. So we consistently work on this to how to improve this, the system to make it also more elegant, like end-to-end, and more efficient. At that time, actually, the SAM model came from, this meta, right? This segment anything model. So we were actually thinking, like, if we can really, combine this with the SAM model, this eye tracking, and instead of like prompt, text prompt, we can use gaze as a prompt. It's very simple system. For, SAM is really working nice for this, computer vision data set, but not really for medical imaging. So we fine-tune and then we put them into the, the eye tracking system. And this was published in one of the nice workshop of, the NeurIPS last year, 2 years ago. And so my students show that actually with gaze, you can do similar stuff like with mouse. This can be useful for, some in some settings, especially for people who need, some some support by, the computer or camera, especially in hospital. And so, this is the computer vision example. They also did for CT scans. It's not bad, so it shows there is a promising angle. If you have a proper, the segmentation, it can be used. Radiologists really like this. They play 1 week or something and they stop playing. So because, it doesn't fit into their clinic yet. But during the surgery, probably it may be easy, nice, with this HoloLens kind of stuff, because they can measure, the tumor, the sum of the other organ, automatically real time on the screen. Just looking at this, this can be possible. This red dot, what you see is actually where the radiologist is looking by eye. And in terms of efficiency, actually, this was like very significantly time reduction, when annotated. So the segmentation results were actually similar with the mouse and gaze SAM and SAM plus mouse. The accuracy was similar, sorry. So again, like I said, we wanted to improve this engineering system, like, although they are connected nicely to each other, still, once you improve some part of them, actually, you just, take that logo and then you work on that part. So can we have like a more effective system in an end-to-end manner? So the idea was actually, we implemented like a graph, separately, but there is an algorithm already, the graph neural networks. Can we do exactly the same thing using these graph neural networks instead of separate engineering way? So the answer is yes. So last year, actually, we completed that work. So we were not the first one really to think about this. Like, can we do eye tracking, especially in the last few years, it becomes more and more popular. A few more centers join this topic of the research. We noticed that actually there are currently 2 solutions apart from what we propose. One of them is actually, as you can see here, the image and this gaze patterns actually, they combine actually, they process separately and then combine. So there is this visual attention map generation. This is the image, this is the normal, the deep learning. And then idea is actually to look at this CAM model. This should be in these existing words, like, they try to minimize it. They try to make them similar. So which we don't 100% agree with this approach. It's a little bit also costly. This is also another approach where there is actually, again, like visual attention map actually generation. So there is no CAM to minimize, but it goes to the encoder and then, the combining with whatever you got from the images. So this is another approach. This is actually little time consuming, but better than the first approach. But it's a single approach, like, better than this engineering way. So what we have done is actually we just also get rid of this VM part, attention generation. Remember, we just model everything. We want to model everything like a graph, so we don't really need generation of this attention map. So what we have done after, we got this gaze pattern, according to like how much they spend time, so this should tell us something about attention. So if there is a tumor or not, if radiologists spend some time there, so there is an interest in that region. So we want to rank those regions and then put them into the deep learning to increase the, the attention of those regions. So yeah, we call it this gaze GNN. So everything is done on the graph neural networks instead of like the graph is separate. So the idea is, again, like, it's very simple. So the gaze is actually, we use the time aggregation as an attention, like a rough attention. And this time aggregation is actually combined with the, the images, and everything is modeled on the graph. It gives us flexibility because you don't really visit every pixels, right? So, and then we try to actually predict the result. This was a diagnostic example using X-ray. I want to show some. This is the time aggregation that I mentioned. Like, the more time spent, it should be actually more attention in that region. Similar to how these transformers are, this patchify, right? You patchify those regions in images. So we do the same for gaze tracking. And so this, the backbone actually, it can be changing. So we find, some optimal backbone working for this case. Again, if there is something else is actually improved in deep learning, probably we can actually, improve this backbone as well. We did actually 3 classification problem for X-ray. One of the reason I just need to also mention this is, we like the GNN, and we compare this with the transformers as well. So as a comparison, the thing is actually with a little bit less data, GNN was working much better. And my favorite part was it is really flexible to represent the different types of information. So for different part of the the graph node, we can add actually more different information. It doesn't need to be the same information. It's really the different vectors we can use. These vectors can include also maybe even some clinical parameters or some report and all other things as well. So we compare this GNN with some transformers and the DenseNet, ResNet model, and actually it improves the backbones from the accuracy side. So if you look at the AUC for different the normal and the pathological case, this chronic heart failure and pneumonia in X-ray, and the average actually you see consistently actually it improves with the attention model, and these are the precision and recall results. Again, like it's better than other backbones. So we look at actually them for the other gaze models in the literature. Again, actually it improves significantly. We choose this chest X-ray data because some of these gaze data were available, so it was easier to to compare. The most importantly, I think from the radiology point of view, if I do gaze, is it better than without gaze, like without eye tracking? So we see like a 3% increase if you include the gaze information in the classification. So this is a significant. performance improvement compared to without gaze information. And this is, so I'm gonna skip this part. In terms of efficiency, if you are interested in, like, gaze GNN is pretty fast compared to other two approaches like attention consistency and two-stream. Two-stream task, you see, it is like 9 seconds. This is pretty long in radiology environment. So one CT scan can finish in 30 seconds. Nobody's gonna wait 10 seconds just for inference time. Okay, so this is the visual example, like what, how gaze tracking may help. So for any given, this chest X-ray images on the right-hand side, so you see one of these, our radiologists look at these regions, and you see the eye gaze map. That is the grad cam with the classification, like without eye gaze integration. So they don't really match a lot. So the computer look at somewhere else, and the radiologist look at somewhere else here, as you can see. The red ones are all the wrong one. Of course, we cherry pick to show, how it improves. So these are the incorrect prediction by the deep learning algorithm. If we integrate, the eye gaze with the deep learning algorithm, you see the grad cam results. Now with eye gaze, actually it starts becoming actually better, and it starts overlapping partially, and the classification turn into green. So initial deep learning predictions were corrected by gaze tracking. So we have also something actually, initially this is pretty easy for engineering point of view, but radiologists find this very useful, is that actually we can show them actually where they look at it and where they don't look at it. So this green part in the the CT scans, it is the part they look at mostly, and the red parts are they don't really look at it. So once the the screening is finished, we show them volume-wise actually where they didn't look at it, and if they want to look at it again, because there may be something there, and we show that actually. So there was one case, very tiny tumor in the region, they didn't look at it. We can show this to them, and they can change their report. If it is wrong, like if it's false positive, we also record this, and they try to update the algorithm, like this is the false positive. So this part actually they like it a lot because it is happening at the end of screening, and they can just change their report. And the results are actually just numerical results. I can say this is better than before. We use eye tracking for many other things as well. One of the the biggest issue in radiology is this ground truth labeling is missing. Large data is not available. We did actually fast segmentation. It's like a rough segmentation. Once we have rough segmentation, we can put them into the better deep learning algorithm to refine the boundary to get the ground truth. We try to put this into the usual routines of the radiologists, so they can look at these tumors, and it can be roughly labeled, and later we can improve the results just for the ground truth labeling. That is this is an environment like I can also show, like it's very flexible environment. They don't have any stress or anything. There is even a coffee there. So this is our the latest eye tracker system. That is not the monitor. Monitor for only that side of, for hours to do some calibration. Another thing, actually, this is important. I think many eye tracking studies are missing. Like, can we use multiple screen? This is very challenging engineering, but we have managed to do that. So we connect everything again engineeringly, and with software we record all this, the motions and the keyboard, mouse parameters. And when radiologists look at different screen, actually we know in which order actually they look at it. So this is one of our earlier work. This is for multiparametric prostate screening. They usually look at the 4 images in 2 screens. And images give you different information, so that's why radiologists look at different images to make diagnosis and treatment planning. So here, you see the 4 different images, and this edge is actually showing how often actually they look at the ADC map, and then they go look at the diffusion imaging, contrast MRI, going back to T2. We have all those information, like in which frequency and amount actually they look at different images, and we can generate the attention map and combine multimodal multi-contrast MRI to do, the prognosis and diagnosis. As a, the side study, again, like at the time, we combined this with the speech recognition to do like weak labeling, finding the tumor and then do the fast segmentation. Now, it's like LLMs are there, so, it's gonna be more advanced model. So this is the, the speech base. Speech gives the, the hint where it is the tumor or not, and then combined with the gaze tracking, actually we can use PET, CT, ultrasound, MRI, all this fast segmentation. Segmentations are here not very accurate, but we don't target that. Rough is okay because later we refine them for ground truth labeling. So before finishing, I'm going to show actually 2 more studies like where we are. We started very engineering way, as you can see. As the field goes, we try to get the benefit of deep learning, combine them, try to make it actually the nicer, faster, more accurate. So recently, actually, we noticed generative AI is everywhere, and the data is a really problem still in medical imaging, and lots of papers about synthetic image generation, synthetic medical image generation, and there is a big excitement about this. Can we use, for example, if you generate 1 million synthetic MR images or CT, can we use them for training your algorithms? Because we never had such big data, right, in medical AI. One of the goals in such studies is to have a very realistic, the image generation. So how realistic they are? So we want to actually look at this topic, and then if with eye tracking, can we potentially improve this generation? So we wanted to actually first, identify the shortcomings of generative AI. So many papers are there. So some of them actually I put here. We have, this one paper for this realistic, the image generation. We have recently one paper, actually, we showed that you don't really need super realistic images to do segmentation. For classification, diagnostic information, yes. But for segmentation, we show it is not, actually. So we did very interesting study with eye tracking. So the main goal was actually to improve these generative AI algorithms. So we ask, actually, so, these papers, actually, when we look at all these papers, numerically, they are fantastic. But clinically, how they are, really, So we want to do this Turing test with radiologists. We asked 16 radiologists to join our experiment. And we use this famous Stanford X-ray data set. They are the one, I think last year, NeurIPS, they published. So far, they are the ones actually look like very realistic and the high quality, high fidelity. They were using this diffusion algorithms. So we asked actually these 16 radiologists in different weeks. The first week, we asked them, can you just read these X-ray images? Some of them are real, some of them are synthetic images, and they don't know if they are synthetic or real. And after a few weeks, we asked them to come and we shuffle images. And we asked them again, okay, some of these images were fake, some of them were real. We don't ask diagnostic test. We asked them, okay, can you tell us which ones are fake, which ones are real? So this was the experiment that we want to use this prior information to improve the generation of these synthetic images. So that is our, the final goal. So the task 1, again, like diagnostic. Task 2 is actually real fake. So the first thing we noticed, like, you can also see here, when we ask, the diagnostic, like no real, no fake, their attention is different. And when you see real fake, it's totally different. So when you put this into the computer, attention is there. Actually, attention doesn't change for computer attention. So it is actually the human attention, this biological attention is task dependent. So we need to be very careful. But it opens a lot of doors for us. So it says that actually we can really personalize AI, based on each radiologist and based on their weaknesses and their, the strengths, instead of using just one AI doing everything. We use this, this Stanford's, this famous algorithm. I think they also use, this computer vision algorithm. to generation of these X-ray images. These are, the different X-ray images, we generated, 10 different, the classes, different pathologies, And then if you look at actually the real fake accuracy of radiologists, so the thing is actually, look at the, the overall accuracy. They are beating the algorithm. So they find most of these cases, the real and fake. You see the real accuracy and the fake accuracy as well. So they are, I can say easily, easily they are identifying which ones are real and which ones are fake. So they may look like, numerically real, but in the clinic, easily they identify. So generative AI is not there yet in terms of, I can say, just from this, the figure, but there is also, some other task as well. So these numbers actually just showing this visual Turing test, the accuracy for different numbers and the gaze coverage, how many percentage of these regions they look at it. So from the radiologist's point of view, this was a success. They were all happy because, many of the time they are also scared, like if AI is going to replace them. No. So what happened actually, this is the beauty part from the engineering and, from the AI side. So we identify from all their, the attention regions where they look at it and they find the fake region. So now we don't have that results yet to show to you, but we are using these regions now to regenerate these parts to make it more real, because these are the one radiologists actually find like unrealistic. So this is actually, we are integrating this into this Stanford algorithm now. So locally we are enhancing to generate actually more realistic. Initial results were very, very good, but we didn't finish experiments. But that was the overall goal of our study. So when the human is in the loop, so the generations are going to be better too. So we will repeat the experiment again with these new generated images. Some of them all understood that we are using them to improve AI. So I don't know if they are happy or not, but the results are getting better and better when the human is in the loop. And the human attention is, again, like I said, it is a task guided. So when you say different, the task, their attention changes. I already said these things. And actually, one more thing I'm going to show, and then I think we can discuss if you have some questions. This part is maybe also very important for you, also for Kaihan. So there is this visual language foundational models everywhere now, right? So our idea is actually, can we use, not always, but when necessary, can we integrate gaze into this system? And then, like for report automation, error detection, diagnosis, and visual question answering. We have some results for visual question answering, diagnosis, and also report automation. Not error detection yet. We have some results, all actually improved almost everything. But so much work actually still needed here. So let's see if we can go from this direction to to make this happen. This the multimodality and all these things are the nature of the the problem. So we believe the human in the loop should be also here too. Thanks to Dali for that picture. This is not new anymore. So this is our actually initial work. Actually, the students asking our model just to to say concentrate on some parts. So we replace this text part actually this question part with the gaze. So the input is gaze, and then we just replace everything actually here. So for X-ray it works. Now we are using our own software for CT and MRI. So this actually work can be used for non-medical imaging applications as well. In vision conferences like Boching, many people show medical. We borrow from computer vision these algorithms. So these guys, I was also with them. We borrowed the idea from medical imaging. So these are the breach, and this crack you can consider them as a pathology, and this breach you can consider them as a medical image. So can you find them and then measure all this, the crack and all this, the pathological part? With HoloLens, we did that. We just minimize, the very simple UNet and also detection algorithm. One of these, the YOLO. And real time, actually, you can just detect, segment, and then also you can quantify. This is especially important when you cannot reach the places easily or danger. For earthquake quantification, actually, you can also do this. So this is another one, like, really human in the loop. So this is another, like, the SPAL. You detect it. You just give the command by text or mouse or just joystick, and then it segments from different angles. It gives you the quantification as well. So very important for civil engineering, the approaches. And so, yeah, human in the loop, actually, as you can see, is many, very beneficial for many things. Lung cancer screening, I show, prostate cancer, many other things we do in our laboratory for this cancer screening. X-ray diagnosis, generation, and personalization of AI-based CAD systems, and real-time segmentation in radiation oncology is useful in surgical planning. It's useful. DALI give me this, the pictures when I say if I do, some increased integration. So far I show you like, the images, right? So in this foundational model, there is a report and other things. So we do this one more experiment actually nowadays. We try to include like the reporting in the screening. So how this affect actually the overall system. It's called multimodal, the AI, right? So, but with GAZE, how it happens. So we want to see how the deep learning algorithms designed for multimodal input can be done with the, in radiology settings. How humans are doing this actually. So in our first experiment, I'm finishing now. In first experiment, we show only images to radiologists to understand like multimodality, how it is processed in their brain. It is a CT images, volumetric, and pulmonary embolism is the topic. So we ask them prognostic question, if these patients are gonna die within 30 days or no. And in the second experiment, after 3 weeks, actually, they come again. We shuffle everything. It is all blind. We also give them the report, like the patient background, the clinical information. All these lab reports are available on the, the left screen. And on the right screen, there is just images. So what happens? So this is exactly what you do in multimodal, even in foundational models, right? What happens? So we notice again, so what happened is that attention changed, biological attention. So in the first experiment with limited knowledge, just images, the clinical guided attention, you just see there 2D and 3D attentions. In the regions for, like, they are looking for pulmonary embolism effect. In the second experiment, when we give them, the patient information, they start looking for like more vital organs and some complementary information. So this is also happening in multimodal deep learning, right? So they are looking for additional information that complement the image information. So this is what we found. And interestingly, reading time decreased a lot. So one scan was 30 seconds. When we say the clinical information, 15 seconds. They are very fast. So this is actually currently what we are working on this now. So how we can do the similar integration within the deep learning. So currently what you do is you give everything to the deep learning and let the algorithm decide how the information is connected, right? So we are actually playing in that area now. So as a prior, we want to give this information, the weight, and then see actually how, if we can really improve this. And again, these attentions also, we want to actually integrate this attention and see actually if we can use only first attention, second, or both, how the results are going to be improved. Again, so another, the future direction we are working on actually the real-time decision making, like if we can get the real-time feedback, human feedback, and then integrate the system. Can we do that? Probably VLM systems we can do, like using large language models. And explainability is, today I didn't touch much, but all this, especially if it is diagnostic or prognostic, we work on a lot on explainability part. Okay, so these are the the future directions that we go with gaze tracking, and these are all my actually collaborators. Thank you very much.
great talk and impressive work.
Thank you. It was a very interesting talk. Yeah, all right.
Yeah.
So I have a question about personalization and potential training of radiologists.
Yeah.
When you were mentioning that that young radiologist had a lot of false positives, that reminded me of a study that happened a long time ago when I was working on lung cancer too, and they found that the senior people were really going through things quickly and weren't calling much, but the young ones, they were so worried that they would overlook cancer that they overcount and over call, and so there's lots of false positives. So I'm wondering, in your system you said like you got a 3% increase when you use gaze in diagnostic accuracy. So that was probably with the real experts and not the trainees, right?
Yeah, these are all 16, all of them are actually expert. For lung cancer study, these were for X-ray. For lung cancer study, we work on novice, middle, and also highly expert people. We work with them too, yeah.
So I'm wondering if in the use case, so if you have your system trained and all this, and now you have this young radiologist who needs to learn more, how would you try to account for that, so that that the maybe the radiologists could be guided also in looking at stuff?
This is very good actually point. Our radiology director is also pushing us a lot for training purpose. We do some work actually. It's a little slow nowadays, but we almost every week actually we do training session with this new radiologist. They come and actually they read, and then we just record them. Actually, from attention maps, we can see their learning curve is very fast because they read a lot of the CT, MRI every day. So our idea was actually not to really guide. Actually, initially it was guide them, but their learning is so fast. So we changed this goal, and actually we just want to learn from them, and then make the algorithm just to complementary to them. So that is a better goal, because like you said, I mean, initially they do like zigzag scanning, not drilling, and they look at almost everywhere. But we saw even in 3 weeks, even in 1 month, this improved a lot. So we talked with statistician, because even statistical analysis was not really possible to compare, because he said there is a learning curve here. So we shouldn't consider them the same person. So so that's why actually we just go, we have models like trying to show them a few things like these blind points. We give them alert, like satisfaction of search may happen, or maybe this is inattentional blinds, or if they're because we know their model, if their model change a lot, we say we ask on the screen like, are you maybe tired or something, because the whole day they read a lot, maybe because of tiredness they are not attention is not there. This happens only when also they go for coffee. Our system says, are you tired, because they don't follow this. So we have such alert to help them as a part of their training, but as a full training, I don't think this is it may not be possible, because their learning curve is so fast. But it's great point. Similar to what you said, we can increase maybe these learning points, like these biases. This happened, that happened. Did you look at that area? So we do that actually for all radiologists. We do that actually, but for novice readers, we do. I mean, it's more questions come naturally.
All right, thank you.
Thank you.
Very nice talk, Ulas. A couple of questions. So I mean, like one follow-up to that question. I guess like you can run a trial, right?
Mm-hmm.
You can run a trial, have the trainees on gaze alert and half the others and see which one learns
Yeah,
faster.
we do that. Yes. We have
Okay.
some information.
So with the trial, you have already accounted for training.
Yes. We do also mix, right? Because of the this learning curve, our statistician actually said that you need to use the half of these people and expert together, clean, unclean, and then another week actually you just mix them up so that we can compare. So yeah, we do that. Yeah.
So so I have two questions. So one question is about the attention map. So I mean there was recently one paper that was saying that there is no reason to believe that the human attention and the attention that comes from self-attention should align with each other.
It doesn't need to be.
Yeah, so it's basically forcing them to be the same probably hurts.
The first one of these first gaze paper was this. They forced them to be aligned. I think it is gonna work only for cases computer and radiologists agree. For these cases, it will work.
Right.
But this is useful when they don't agree. Especially those cases computers focus on the false regions, or maybe that particular image may be out of distribution, maybe falsely learned. For those cases, actually human gaze helps.
Right.
But for regular cases there is a very big tumor, everybody look, even computer look, there is no meaning of using gaze.
Yeah. Also, the reason for human attention and self-attention are kind of different. So, our system is optimized to minimize energy consumption of the brain.
Yes.
And that's not the case about
True.
neural network.
I totally agree. So, initially when we start this, we were thinking that can we make the system human-like, but we know that humans are also not perfect.
Yeah.
So that algorithm actually is trying to make these two systems are similar. I think that is also wrong. So that's why we just don't touch these two topics. We just want them to complementary. Just use both of them. It is gonna be helpful only when they are there is a case out of distribution, false. The algorithm is not able to define those things. It's gonna work. For there will be things where computer is gonna be better too, especially when radiologists have a lot of bias. Their gaze system can reduce the deep learning things as well. But this is the drawback, the only drawback.
So, and then my last question is about the generation. So this task is a little bit difficult to do in 2D because in 2D amount of details that you see is very small. But so when you're synthesizing 3D, we did a Turing test, and what we saw here is that when you are testing basically running a Turing test for the generative model, when you are asking the radiologist, the prompt that you provide to radiologists actually matter. If you ask them, for example, to assess the realisticness of a vessel, the performance of them detecting the fake versus real is very different than when you ask them, for example,
this is a good point,
fissure
actually.
lines.
No, I think this is nice. I like it. So asking more localized questions, I think it's going to be better. Perfect, yeah. Even nodules and pathology, continuation of these vessels and all those things. Yeah. And they still look at the big images, right?
They look at the
Okay.
But if you prompt them just to look at the fissure lines,
okay, I think... thank you very much. This study was not published yet, so I will add this. This is good point. Yeah, before reviewer ask. Nice.
I'm not the R2.
This is good. This is good.
Great, thanks.
So I like this idea that you convert the gaze coordinates into input into the language model. So I was wondering, what if you interpreted the gaze nodes in your graph and in terms of the anatomical information you have about the scan. So this radiologist is looking at the apex or is focusing on the region near the fissure, and then use that language as an input into the language model. Do you think that would help?
Yeah. So my student did actually for the X-ray part, he divided the X-ray into 22 regions in the background. So we know this anatomical part. already, the label. So when the radiologists look at specific part, we already know that anatomy, and that goes into the report. If there is also something abnormality goes there, so it automatically goes. So we do that for X-ray, probably easier. For CT and all other, we will see. It's gonna be more difficult, yeah.
I'm working on that too. we have a kind of like a visual prompting project. So we have a more versatile UI for a vision angle model. So they can interact with people from all different modalities, maybe the gaze as well in the future. Do we have more questions? I will save my question to offline, but I can end this talk with a comment. Not a comment, a story I can share. When I was visiting Ulas group in Northwestern, so one radiologist was actually running some experiments in your lab, like gaze tracking experiments, and they are screening all different X-ray or MRI. I'm not sure. I'm still learning about that. After they finished that, Ulas told me, you know what? One of them actually was generated by AI. They didn't actually spot that. So I was really amazed that the research is really serious about patients, about medical applications, but you're making ensure people, students, they can still have some fun from the research experience. So that's amazing.
Thank you.
Thank you so much again. Thank you all for coming.
Thank you very much for coming. Thank you.